So now we know what is the condition for small signals, and we also know how the circuit should look like for small signals. So this is how it should look like for small signals. Let's try to see how to go and bias this transistor. First, let me draw the small signal picture. So this is my small signal source. I directly connect it, and then I have the load. I'm just redrawing the same amplifier we had, but this is only for small signals. But I have to make sure that the transistor is biased in which region? Saturation. So which means if I try to find the DC operating point, this should remain in saturation region. And what is the condition for saturation region? VGS greater than VTH and VDS. Okay. So which means I should make sure that the transistor is operating with sufficient gate to source voltage as well as sufficient drain to source voltage. So let's say I give you all sorts of ideal voltage sources. The simplest thing you would do is hook up a DC source, say some VA. Make sure the VGS is sufficient. Put another voltage source, say VB, and make sure that the VDS is sufficient. But remember, this is the circuit only for DC operating point, but in small signals it should look like this. So let's try to combine the two and draw the total circuit, how it should look like. So now the one thing that doesn't change in the two circuits is the transistor. So let's draw that first. That's simple. Now I have the small signal. Let us say V in and RS. Draw it again. Now I can't go and connect it directly because then the operating point VGS is basically 0. So remember, the small signal voltage here is V in, right? But what should be the total voltage that the gate should see? V in plus VA, right? I want at the operating point the gate should be VA. For small signals it should be V in. The total should be V in plus VA. Is that clear? Now of course if I give all sorts of voltage sources, ideal voltage sources, I have V in, I want to shift it by VA. I have voltage sources with the value VA. What do? I have to add two voltage sources. How do you add two voltage sources? You connect them in series. So if I go and do this, so this should be having a voltage. Done. Now let's look at the load. So this is, let us say, the load. Sorry, let me draw the DC source. This is the VB. I ideally want to connect it to the drain, but of course I can't directly connect it to the drain because then I'll have to connect the load somehow. So and for small signals, what can you say about this DC source? It is short. And for small signals, I want to make sure the RL is connected between drain and the small signal ground. So I have to connect RL from drain to a small signal ground. Where can I connect now? See, one end of RL must be here. Other end of RL must be at a small signal ground. So where do you think I can connect? To connect it to? Series or parallel? Okay. let's erase this. You say you want to do it parallel, is that correct? Because for small signals drain is incrementally short. That's not what you want, right? So how should we connect it? But there is one change you have to do. See, in the operating point picture I have drawn here, what is the VDS? What is the value of VDS? VB. But here what is the value of VDS operating point? Is it VB? VB minus? Yeah. So the operating point VD I get now is VB minus the drain current times RL. So which means I cannot use VB here. This value should change from VB to, I mean, what I'm saying is, ideally you want the drain to source voltage to be a value VB. But the moment I hook up this circuit, because there is a drop across RL, I'm losing VB minus some ID RL. Let us say, for example, 500 millivolts I'm losing because of RL. So how should I change my VB so that I get back the same voltage? I should compensate the drop by increasing the voltage source. If I change it to VB plus IDRL, now there is going to be a drop of minus IDRL. Is that okay? Of course, I will not worry about this additional change, so I will call it some VB hat. Okay. So this is something that will work definitely, and this is what we call the common source amplifier. Because again, if we look at the two-port thingy, so this is the common terminal in my two-port, and the common terminal here is this clear? How did we bias this for now? Any questions? Okay. So unfortunately, although this works, there is a lot of practical difficulties with this. Because as engineers, you should have challenges. Otherwise, what is the point? Okay. So one of the first problem is this. Here I have assumed that I have a voltage source wherein I can access both the negative and positive terminals of the voltage source. But in practice, it turns out all the voltage sources are such that the negative terminal is grounded. You don't have access to both negative and positive terminals of your voltage sources. So let's say this can be your Vn. So which means I cannot do this, right? So that's a practical problem, that's all. So let's see how to circumvent this problem, and for that let's understand what a voltage source is. So what is a voltage source? If you want to explain what a voltage source is in English, what would you say? Correct? Exactly. It makes sure that the voltage is constant irrespective of the current drawn from it, which means it can provide any amount of current, which means it can provide any amount of charge. So which means if I ask you how much charge the voltage source is storing, what would be your answer? Infinite. So do you know any other element that can store charge? Capacitor. Right. So now it seems like I have a voltage source. I know this is going to contain infinite amount of charge. If let us say I have a capacitor charged to the same voltage, and if this capacitor must have infinite amount of charge, what should be the value of the capacitance? I mean, Q is C times V. V is fixed. So if the charge has to be infinity, what should go to infinity? So if the capacitance value ideally tends to infinity, this is same as having an ideal voltage source. Is that clear? So if let us say C1, and if this tends to infinity, this basically behaves like an ideal voltage source. Of course, I can't have an infinitely large capacitor. In practice, we should have a large capacitor How large it is we'll see later, but at least to start with, this seems like a good option. So I'll replace this with what now? And what should be the value of the capacitance ideally? Infinite. So I'll call that C1 and assume that this is actually an infinite capacitor. And this should be charged to the same voltage VA, right? Is this clear? Now it turns out you cannot just have a capacitor charged to a voltage and connect it like this thinking it will work, because in practice all capacitors have a leakage resistor associated with them. You might not be able to see it with your eyes, but that's how the structure is. So which means the resistor will slowly suck away all the charge, you lose out. Okay. So I cannot assume that I will charge the capacitor once and let it be there. I should make sure that I am continuously charging the capacitor to the required voltage. And we don't have to worry because we have this voltage source VA with us. Of course, this terminal is grounded. Now I want to make sure that the capacitor is charged to VA. So what do you suggest we can do? I connect. Looks like this is what I should do. But if I do that, what can you say about the total gate voltage? This voltage source will go and fix the voltage at the gate to be VA. But is that what you want? What should be the total gate voltage? The DC plus the small signal. So I can't directly go and connect it, right? But of course I have to connect it somehow because I have to charge the capacitor to VA. So what can I put in between? I mean something that makes sure that this node doesn't get shorted to it. What is the simplest element you can think? You can put a resistor. I'll call it, say, maybe RB, bias resistor. Now we still don't know how much should be the value of RB and stuff, but looks like if I do this, you're okay. So we are thinking this will be fine, but let's confirm that this is indeed okay. For that, let's understand how this part of the circuit operates. Now remember, what is the gate current drawn? 0. So which means I can only consider this part in isolation and see if the voltage at the gate is fine or not, right? So I'll draw this part of the circuit alone separately. So this is a small signal. This is RS, and what we are saying is we'll have a capacitor and we charge the capacitor with the DC voltage source V. Okay, right. And this is my gate voltage VG, and ideally I want my gate voltage to be VA plus Vin. Let's see if it works, right? So now this is a linear circuit or a non-linear circuit? Look at the circuit, linear or non-linear? Linear? We just have resistors, capacitors, voltage source. It is a linear circuit. I have linear circuit, I have two voltage sources as inputs. How would you solve? Use superposition. So I'll consider one voltage source at a time and find what is the response, and then sum up the response. So first let me actually consider say only the DC, right? So I'll assume that the other voltage is 0. So this is only due to VA. Now, so in this case, what should be VG be equal to? Ideally, what do you want it to be? Should be equal to V. This is what you want, but let's confirm if it's the case. Now remember, this voltage is essentially the voltage drop across the capacitor and this resistor. Now look at this, I have a simple RC circuit that's getting charged with a DC voltage source VA. So in steady state, what do you think the voltage across the capacitor will be? The capacitor will get charged to, is that clear? the capacitor will eventually get charged to VA. Is that okay? Now in steady state, what is the voltage drop across RS? Why not? Why is it non-zero? Yeah, steady state. So why is it 0? Okay, I'll ask you, why can't the capacitor charge more than VA? Okay. Why is the capacitor open circuit? So? Huh? I mean, everyone, okay, I'm agreeing to the fact that, let us say, the maximum it can charge is VA, but why can't, why should this voltage be 0? Why should this behave like an open circuit?
Because it is charged sufficiently so that no current is flowing.
Why can't more current flow through it? What will happen? Or if, in other words, if I ask you in steady state, what is the DC current flowing through the capacitor? Why can't it be non-zero? Correct.
That on a point of time that we call steady state, the potential difference, the source side and the capacitor considered as a battery for some time, it will also charge the same voltage. VA minus VC by R net.
Yeah. So I mean, so which means in steady state, what is the DC current flowing through capacitor? That's all correct. But what is the steady state current through the capacitor?
0.
Is it clear? So if the steady state current through the capacitor is 0, what is the voltage across RS?
0.
Is it clear? Again, remember that, see, what is the voltage current relation for a capacitor? If I know, for example, I mean voltage current, not Q. What is voltage of the capacitor? 1 by C? Fine. Now, if let us say a DC current flows through the capacitor, so which means this current is constant. So what will happen to the voltage? It will eventually keep increasing. So as long as you know the voltages in your circuit are all finite, in steady state, the DC current flowing through a capacitor is always 0. Okay. So it doesn't mean that capacitor is always like an open circuit. I mean, there's a misconception that capacitor blocks DC and stuff. That's not true, because I can push in a DC current through a capacitor. The capacitor will happily allow the current to flow. What will happen to the voltage though? So only if you are sure that the voltages in your circuits are all finite, then you can claim that the average current is 0. Okay, is this clear? If I say voltage across a capacitor is 1 by C integral I dt. If there is a DC current flowing through the capacitor, this is a constant, which means this is going to be a ramp, which means the voltage across a capacitor will grow unbounded. But that's not the case in your circuit. So as long as you know the circuit is stable and none of the voltages blow to infinity, it is guaranteed that the DC current in steady state through a capacitor is, but it doesn't mean that a capacitor blocks DC. That's a misconception I want to clarify. Because I can always pump in a DC current source through a capacitor. The capacitor will, allow the current to flow, but the response will be the voltage will blow to infinity. Is that okay?
But if I is 0,
Yeah, I is 0.
then what about VC?
Phi is 0. Yeah, tell me, if there is no current, what is the voltage across capacitor now? I mean, okay, what is, if this is basically giving you a capacitor and asking the voltage across a capacitor. What will you say? 0, or can you always say it's 0? Huh? Yeah, I mean, whatever the voltage to which the capacitor was charged to before, that's going to be the same. You're not drawing any current, the capacitor will not lose any charge. So whatever the voltage to which the capacitor was charged to before, it's going to return. Anyways, so we digressed a lot, but now it is sure that my Vg is Va. That is it. So we have computed the response due to Va. Let's quickly do to Vin and wrap it. So let's try to find due to Vin. So if I'm trying to find U2 V in, this is V in, and oops, I'll make VA to 0. Okay. Now what is the impedance offered by capacitor in frequency domain? 1 by? Everyone remembers? Now let's start with, let's assume that the capacitor is infinitely large. Then what can you say about the impedance? I mean, the capacitance value is infinitely large. So what is the impedance? So I can treat it like a short circuit. Then can you tell me what is the gate voltage now? RB by times. Ideally, what do you want this to be equal to? You want the gate voltage to be V in. So that directly gives you a condition on RB. How should RB be? I mean, you want this fraction to be how much? Yeah. Large means, I mean, large is a relative term. Relative to what it should be large. Right? Remember that when I say small, large, short, tall, everything, it's all a relative term. With respect to 10, 1 is small, but with respect to 0.1, 1 is large. So this gives a condition on RB directly, so we know what to do. Let's quickly do for C and we'll wrap. So now let's include the effect of C. Now you have the capacitor offering an impedance 1 by j omega C. Let's try to do it in the frequency domain. If I write it as Vg of j omega, now we'll have a voltage division between Rs, this impedance, and Rb. What is the division factor? Rb by plus times V in of j omega. Everything is in the frequency domain. Now I already know that this should be approximately 1. So then what can you say about the impedance of the capacitor? If you look at the magnitude of the capacitor impedance, how should that be compared to? Right. So which means I'll find C1 is much greater than 1 by omega times. Is that okay? And remember that I know what is my input. So in my input I'll find what is the minimum sinusoidal frequency I have. I use that minimum to get the absolute limit on C. Remember, omega is a variable, right? I should use a value for the variable. I know what is the range of frequencies my input will have. So to find the maximum capacitance I should have, or the minimum, sorry, to find the minimum capacitance I should use, I'll take the minimum value of 1. Sorry. Is that okay? So we'll stop here and we'll continue.